So here we go with part 2 of CCEA AS Unit 1 for Physics 2022, and then part 2 is questions 6 to 8. So 1 to 5 were like the mechanics questions, and these are like mainly the electricity stuff. Okay then. So question 8, a battery with EMF. Oh, hold on. This is not the right question. We might be on 6. Okay, this is more like it. Standard twin core and earth cable consisting of 3 copper wires is used by an electrician to connect a 9.50 kilowatt electric shower to the 230 volts main supply. Calculate the current drawn from the main supply when the shower is used at maximum power. Okay, so they've given us the power, they've given us the voltage, so we need an equation that has that, and they're interested in current, so we need a power and voltage and current equation. So we know that power equals VI, so I is going to be P over V, and that's going to be 9.5 kilowatts over 230 volts, and that's giving us 41.3 amps. Calculate the electrical energy used by the shower if it is turned on at maximum power for 10 minutes. So we have a power and we have a time, so we should be able to work out an energy. So energy used is going to be power times time. And remember that we need time in seconds and power in watts. So 9.50 times 10 to the 3, and then multiply by 10 times 60 to give the total number of seconds in 10 minutes. And that gives us 5.7 million joules. Part 3. Calculate the number of electrons passing a point in the circuit of the electric shower during these 10 minutes. Okay, so again, we've got a current, we've got a time, so we should be able to get a charge from that. Q equals IT. But the number of electrons also equals Q over E, the elementary charge. So N will equal IT over E, and we just sub into that now. So we've 41.3 amps, 600 seconds, and the charge of an electron is 1.6 times 10 to the minus 19. And you can see that it gives us approximately 1.55 times 10 to the 23. Okay. The electrician uses a 15-meter length of the twin core and earth cable to connect the shower to the main supply. Each of the 3 copper wires has a diameter of 2.76 millimeters. The resistivity of copper is 1.72 times 10 to the minus 8 ohm meters. Define resistivity. Okay, so this is again straight from your notes. So it's the resistance of a sample of material where you basically make the length 1 and the cross section 1. Okay, so with a length of 1 meter and a cross sectional area of 1 meter squared. Some people talk about it being the resistance across a cube of the material that has length, width and height 1 meter, because that would guarantee you a 1 meter squared area and it being 1 meter long. Calculate the resistance then. So we have an equation for that, and it's that R is rho L over A. And we can think of A as pi R squared or pi D squared over 4. So R would then be 4 rho L over pi D squared. And it should be possible just to sub into that now. So we've got 4 times rho of 1.72 times 10 to the minus 8 times the length of 15 divided by pi times d squared. Okay, so d is in millimeters, so we need to put a 10 to the minus 3 in there before we square it, so that it's being squared after it's been changed into meters. And that comes to 0.0431 of an ohm. Part C then. 2.76 millimeters is the recommended diameter of the wire to be used. Explain fully why it would not be good practice to fit the 9.50 kilowatt shower using a 15 meter length of a cable with a wire of smaller diameter. Okay, so this is all about the fact that basically electrical flow of current produces heat, and if there's any significant amount of heat, then you're going to have the danger of like the insulation melting on the wire and then it's sparking and stuff like that, so it could cause an electrical fire. So it's sort of it's a safety issue. We want to talk about the physics properties of it, and the physics properties of it is if we make the diameter smaller, the resistance will increase, and that will increase the heating of the actual cable carrying the energy to the shower. Okay, so a smaller diameter cable will produce a wire with higher resistance, causing it to heat up, which would be dangerous. I suppose you could say heat up more, just so that you're clear about that. Question 7. A student is asked to perform an experiment to determine the EMF and internal resistance of a battery from a graph of the results. So they're very clear about what they want you to do. In the space below, draw a circuit diagram of the setup the student would use. So again, this is straight out of one of your standard experiments. So you have your EMF of the cell and the internal resistance, little r of the cell, and that's all contained within that cylindrical object that we buy in a supermarket and call it a battery, when in fact it's actually a cell. The wee cylinder shaped things we buy are called cells. They only become a battery when you combine them together. But yeah, that wee shape contains the EMF and the internal resistance. So let's label those. Now in the standard experiment, we want to put a voltmeter across that, and we want to put an ammeter in series with it. And then we want to weigh a varying both V and I, and the way to do that is to introduce a variable resistor. And you probably also want to introduce a switch, because you don't want to be drawing current all the time from a cell that you're doing an experiment on, because if you drain it, then your later results won't be consistent with your early results. So you want a variable resistor and a switch. And that's your circuit ready to go. And so the idea here is that every time you adjust the variable resistor, you get slightly different values of voltage and current. So the second part then, it says, is describe the procedure that would need to be carried out. And we pretty much already covered it. You know, you keep adjusting the variable resistor to get various values of voltage and current, and you want to take a reasonable number of those in order to get a decent graph. Okay, so we want to record a range of values of voltage and current. We get those, and we want at least about 5 of them by adjusting the variable resistor. So now they want us to show what the graph would look like. Okay, so if we put voltage up the side and current along the bottom, again being sure to put units on them. So voltage is in volts, current I is in amps. And then if you remember from your notes, what we get here is a downward slope. Something like that. So the EMF comes from the voltage here when current is 0. So this intercept is the value of the EMF, and the gradient is a negative copy of the resistance. So it's like -1 times it gives you the resistance. So state how the EMF and internal resistance could be obtained from the graph. So the EMF is just the intercept on the voltage axis, and the resistance comes from, well, that should be little r really, and the resistance comes from the gradient times -1, just the negative of the gradient really. So you can sort of get that analysis from rearranging your equation to match what we've got. So we're plotting V versus I, so we want V equal to something times I, and then we find that we've got plus E there as well, and that's where the intercept is coming. And that's sort of the idea here, very much, that when the current is 0, V becomes equal to E. That's why you get the intercept. And then in the meantime, -r is the gradient. Question 8. A battery with EMF 12 volts and internal resistance r is connected to a potential divider circuit containing a negative temperature coefficient NTC thermistor and a 30 ohm resistor as shown. The circuit is operating at room temperature of 18 degrees C. The resistance of the thermistor is 20 degrees at this temperature, and the output voltage V out across the 30 ohm resistor is 7.12 volts. Okay, so I've just added on a little bit of what they have told us. They've told us that the output voltage is 7.12 volts across this 30 ohm resistor when the circuit is set up like this. Now the thing is that these two, the 30 ohms and this, should allow us to work out the current here, and that will be the current in this entire loop. So if they are asking, as they probably are, us to find the value of little r, then we can do that several ways. You can just fill in your potential divider circuit, remembering that little r counts as one of the parts of that resistance that are total. Or you can just say, well, we'll get the current, and then we'll say that the 12 volts here, that V equals I times all of this R. So I can say that R total is 50 plus little r, because there's a 20 and a 30 and little r around the loop. So the total resistance is the sum of them all because they're in series. So 50 plus little r is the total resistance. We can get the current from those two values that we know there, the 7.12 and the 30 volts. So we can get current from that. So I is V over R for the R1 resistor. And that's going to be 7.12 over 30. And that's 0.237 of an amp. So we can now use V equals IR on the entire circuit. So V will equal IRT, where V will use the 12 volts of the EMF, the source of voltage in the circuit, and RT is what we said it was, 50 plus little r. So dividing by I, we get V over I equals 50 plus r, which means that V over I minus 50 should equal little r. And I'm getting a 0.633, I suppose, for that, which is quite far from what the mark scheme says. But I think that because there's a big subtraction going on here, small differences in that subtraction may produce a discrepancy in this value. So I'm going to trust my value of 0.633. The temperature of the room increases to 28 degrees C. Complete table 8.1 by ticking the correct option to state how the output voltage across the 30 ohm resistor will be affected, if at all, by the change in temperature. Okay, so this is a negative temperature coefficient thermistor. So when it gets warmer, the resistance of that will decrease. And that will cause the fixed resistor to be a bigger fraction of the total resistance. And so the value across it would increase. So because the resistance across the thermistor decreases, then as a fraction of the total resistance, the 30 ohm becomes a bigger fraction, and that means it'll get a bigger fraction of the voltage. A practical use for this circuit, some kind of temperature control. So some kind of like thermostat circuit. So some kind of application, e.g. a thermostat opening a window when a room gets too warm. Okay, and that's that. Hope that's been helpful to you. Thanks for watching now.